September 17th, 1917. Ypres-Salient, Belgium. Major Peter Norman Nissen stood in knee-deep mud, watching Canadian engineers struggle to erect yet another timber barracks in rain that hadn't stopped for 11 days. The wooden frame was already warping, the canvas roof leaked at every seam. In 3 weeks, maybe 4, the structure would be rotting from the inside out, and another crew would waste another week tearing it down and starting over. Before we jump back in, tell us where you're tuning in from, and if this story touched you, make sure you're subscribed because tomorrow I've saved something extra special for you. Behind him, stretching toward the horizon, lay a landscape that had ceased to resemble anything human. Artillery craters filled with water, shattered trees reduced to splinters. The Western Front had become a machine that consumed men and materials at rates no peacetime mind could comprehend. The British Expeditionary Force alone numbered over 2 million soldiers, and every single one needed shelter, not luxury, not comfort, just 4 walls and a roof that would keep them alive through the Belgian winter. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem wasn't manpower. Britain had engineers. The problem was time and timber. A standard wooden barracks required 2 weeks to construct, used 30 tons of lumber, and began deteriorating the moment it was complete. Multiply that by 10,000 structures, and the mathematics became impossible. The British were building accommodations slower than German artillery was destroying them. Nissen had been watching this failure for months, assigned to the Royal Engineers Experimental Works in early 1917, with orders to solve what everyone called the shelter crisis. He was 31 years old, a Canadian-born mining engineer who'd spent years in the United States designing industrial structures before the war pulled him back across the Atlantic. His specialty was unusual for military engineering. He understood how materials behaved under stress, how steel could be shaped, how geometry could replace mass. The Western Front needed revolutionary thinking, and the British Army, desperate enough to try anything, had given him 6 weeks to produce results. September meant 6 weeks until November. November meant winter. Winter meant tens of thousands of soldiers would be sleeping in canvas tents or rotting wooden shelters, while German troops sat in concrete bunkers 50 yards away across no man's land. The inequality wasn't just uncomfortable. It was lethal. Pneumonia killed as many British soldiers in the winter of 1916 through 17 as some battles. Trench foot, dysentery, influenza, all thrived in the cold, wet conditions of inadequate shelter. Nissen returned to his workshop at Ypres that evening and cleared his drafting table. Around him, other engineers worked on standard problems: bridge repairs, trench reinforcement, railway construction. Nissen was after something else entirely. He needed a structure that violated every principle of traditional architecture. It had to be light enough to transport in pieces on the Western Front's overwhelmed rail network, strong enough to survive artillery concussion and winter storms, simple enough that ordinary soldiers, not trained carpenters, could assemble it. And it had to be fast, not days, hours. The solution appeared in his mind fully formed, arriving not through systematic design but through a single insight about geometry. What if the walls and the roof were the same thing? Traditional buildings used walls to hold up a separate roof structure. 2 distinct systems, 2 distinct failure points. But a continuous arch, a half-cylinder laid on its side, was self-supporting. Every part of the curve carried load. There were no weak points because there was no distinction between wall and ceiling. Nissen began sketching rapidly. A semicircular profile, approximately 16 feet in diameter. The curve would be formed from corrugated steel sheets, lightweight but rigid because of the ridges stamped into the metal. The sheets would attach to a simple internal frame, wooden ribs spaced every few feet along the length. No complex joints, no intricate carpentry. Just curved steel panels bolted to a skeleton of wooden hoops. The length could vary depending on need. 30 feet for a standard barracks housing 25 men, 60 feet for a mess hall or field hospital. The principle remained identical: extend the half-cylinder as far as necessary, then close the ends with flat wooden walls containing doors and windows. The entire structure would sit directly on the ground or on a simple foundation of wooden boards. No deep footings, no concrete, no engineering surveys. Put it where you need it and move on. For 3 days, Nissen worked 16-hour shifts, refining the concept on paper. The corrugated steel panels would be 4 feet wide, 8 feet long, light enough for 2 men to carry, small enough to stack efficiently for transport. Each hut would require approximately 50 panels plus the wooden rib structure and the end walls. Total weight, less than 2 tons. A single railway flat car could carry 5 complete huts broken down into components. The ribs presented the first major problem. How do you create a perfect semicircular wooden frame when you're working in a war zone with no specialized equipment? Nissen's solution was elegant. Instead of bending wood, which required steam and time and skill, he designed the ribs in 3 sections, 2 curved sides and a flat cap at the top. The curves could be cut from straight planks using simple patterns. Nail the 3 pieces together, and you had a 16-foot diameter hoop strong enough to support the corrugated covering. By September 21st, he had finished drawings. By September 23rd, he had authorization from the Director of Army Contracts to build a prototype. By September 26th, materials arrived at WWII, 2 tons of corrugated steel sheeting, 1,000 board feet of timber, 300 pounds of nails and bolts, and a crew of 8 Royal Engineers who'd never heard of Peter Nissen and had no idea why they were about to spend the next 2 days building what looked like a steel culvert big enough to walk through. The test location was a muddy field 5 miles behind the front lines, far enough to be relatively safe from artillery but close enough that the constant rumble of guns was audible day and night. Nissen arrived at dawn on September 27th and found his crew standing around the stacked materials, smoking cigarettes and looking sceptical. Sergeant William Davis, a Welsh carpenter in his 40s who'd built houses in Cardiff before the war, examined the corrugated steel sheets dubiously. "Sir, are we building a shed or a sewer pipe?" "Neither," Nissen replied. "We're building a barracks. It'll house 25 men. And if we do this right, it'll go up in 1 day." Davies glanced at the other engineers. A day's work back home meant framing a single room, maybe laying a floor. Now, this Canadian officer was claiming they'd erect an entire building before sunset. The instructions Nissen provided were refreshingly simple. First, lay wooden boards on the ground to create a floor roughly 16 feet by 30 feet. This kept the interior dry and gave them something to attach the rib structure to. Second, assemble the wooden ribs. Each rib was built from 3 wooden pieces nailed together to form a semicircular hoop. 8 ribs total, spaced roughly 4 feet apart along the 30-foot length. Third, stand the ribs upright and secure them to the floorboards. This created the skeleton, 8 wooden hoops marching in a line like the ribs of some massive steel beast. Fourth, attach the corrugated panels. Start at the bottom of the curve, where the ribs met the floor. Bolt the first sheet to the ribs, then overlap the next sheet by 1 corrugation and bolt it in place. Work upward on both sides simultaneously until the panels met at the top of the arch. Fifth, close the ends with flat wooden walls. Simple framing, a door at each end, windows if desired. Sergeant Davis and his crew worked steadily through the morning. The wooden ribs went up faster than expected. With no complex joinery required, just nailing 3 pieces together, each rib took about 20 minutes to assemble. By noon, the skeleton stood complete, 8 hoops creating a tunnel of wood that looked strangely prehistoric against the scarred Belgian landscape. The corrugated panels proved more challenging. Each sheet weighed roughly 30 pounds, awkward but manageable for 2 men. The trick was holding them in position while a third man drilled holes and inserted bolts. The corrugations made the panels rigid along their length but flexible across their width, which meant they naturally wanted to curve. This was intentional. Nissen had calculated that the 4-foot wide panels would adopt the 16-foot diameter curve almost perfectly when forced against the wooden ribs. By mid-afternoon, The first 5 panels were in place on each side, forming a steel shell from ground level to about 8 feet up the curve. The structure was beginning to look less like construction and more like architecture. The smooth arc of corrugated steel caught the pale September sunlight, reflecting it in horizontal lines where each panel overlapped the next. At 4 o'clock, a British colonel drove past in a staff car, spotted the unusual structure, and stopped to investigate. He walked around the half-completed hut twice, hands clasped behind his back, saying nothing. Finally, he turned to Nissen. "How much weight can it carry?" "As much as the ground can support," Nissen replied. "The arch distributes. Load evenly. There's no single point of failure." "What if artillery lands nearby?" the colonel asked. "If it's a direct hit, nothing will help. But blast over pressure? Shrapnel? The curve deflects force instead of resisting it. The Nissen design should survive anything that doesn't physically tear through the steel." The colonel grunted noncommittally and drove away, but word spread quickly through the military bureaucracy that something unusual was happening at Ypres. By sunset, the prototype stood complete. Sergeant Davies and his crew stepped back, covered in mud and metal filings, looking at what they'd built in slightly under 9 hours of work. The structure measured 16 feet wide, 30 feet long, and 8 feet high at the center of the arch. From the outside, it resembled a half-buried pipe. From the inside, it felt surprisingly spacious. Nissen walked the interior slowly, running his hand along the corrugated steel walls. The panels had seated properly against the wooden ribs. No gaps, no buckling. The overlap between sheets was tight enough to shed rain. The end walls fitted cleanly into the arch. 2 doors allowed cross-ventilation. 3 windows on each side let in natural light. The floor was solid planking, raised slightly above the muddy ground. It wasn't beautiful. It would never grace the cover of an architecture journal, but it was functional, efficient, and fast. 9 hours from bare ground to complete shelter capable of housing 25 soldiers. Sergeant Davies stood in the doorway, studying the curved ceiling. "Bit like sleeping inside a barrel, sir." "Better than sleeping in a tent in November," Nissen replied. "Better than dying of pneumonia because we couldn't build shelters fast enough." Over the next week, the prototype underwent field testing that would have destroyed most temporary structures. On October 1st, a German artillery barrage landed half a mile away. The concussion was strong enough to rattle equipment inside the hut and crack one of the window panes. The structure itself showed no damage. The arch had flexed slightly, absorbing the shock wave, then returned to its original shape. On October 3rd, heavy rain fell continuously for 18 hours. Water pooled around the base of the hut but didn't penetrate. The overlap between corrugated panels shed moisture efficiently, and the raised wooden floor kept the interior dry. On October 7th, engineers deliberately overloaded the structure, stacking 2 tons of sandbags along one side to simulate asymmetric stress from wind or partial collapse of an adjacent building. The wooden ribs flexed but didn't break. The bolted connections between steel panels and wood frame held firm. When they removed the sandbags, the hut returned to its original shape with no permanent deformation. The test that mattered most came on October 10th. 25 soldiers from a Canadian infantry battalion moved into the prototype as their actual living quarters. They brought personal equipment, set up cots, hung lanterns from the wooden ribs, and lived in the hut for 5 days, while military observers documented their experience. The soldiers' feedback was consistently positive. The interior stayed noticeably warmer than canvas tents due to the double layer of steel with an air gap between the corrugated outer skin and the wooden ribs. Condensation was minimal compared to canvas, which became soaked from human respiration in cold weather. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The curved ceiling was initially strange, but proved practical. Men quickly learned where they could stand upright and where they needed to duck. Tallis soldiers simply positioned their cots toward the center of the hut, where the arch gave maximum headroom. The structure felt solid in the wind. Canvas tents flapped and flexed, and kept soldiers awake. The Nissen Hut, it was silent except when rain drummed on the corrugated roof, a sound several soldiers described as oddly comforting. On October 16th, Major Nissen submitted his final report to the Royal Engineers headquarters. The document was 12 pages long, filled with technical specifications, material costs, and assembly timelines. But the conclusion was simple and direct. The Nissen Hut represented a revolution in military construction. One prototype had been built in 9 hours by 8 men. With refinement of the assembly process, Nissen estimated a trained crew could erect a standard hut in 6 hours. Material cost per unit was approximately £30, 1/3 the cost of a comparable wooden barracks. Transport requirements were minimal. 5 huts could ship on a single railway flat car. Most critically, the design required no skilled labour. Soldiers with basic tools and simple instructions could build their own shelter. This meant construction could proceed simultaneously at dozens of locations instead of being bottlenecked by the availability of trained carpenters. Within a week, the British Army placed an order for 100 Nissen huts to be manufactured immediately for deployment to forward areas along the Western Front. Within 2 weeks, that order increased to 500. Within a month, the number reached 1,000. The challenge shifted from design to production. How do you manufacture 1,000 huts when Britain's steel mills and sawmills were already operating at maximum capacity supporting the war effort? Nissen's solution was to decentralize production. Instead of building the huts at a single factory, he licensed the design to multiple manufacturers across Britain. Sheet metal fabricators could produce the corrugated steel panels using existing equipment. Sawmills could cut the wooden components using simple patterns. Even small workshops could contribute by manufacturing the bolts and fasteners. By December 1917, Nissen huts were arriving at ports across France and Belgium at a rate of 50 per week. Assembly crews, trained in the now standardized construction method, could erect a complete hut in under 6 hours. Along the Western Front, rows of curved steel shelters began appearing wherever British and Canadian forces established positions. They served as barracks, mess halls, field hospitals, ammunition storage, vehicle repair shops, communications centres, and command posts. The huts weren't perfect. Interior temperatures in summer could be brutal. The steel absorbed heat during the day and radiated it into the interior, creating an oven effect that made sleeping difficult. Soldiers learned to drape canvas over the roof to provide shade and reduce heat buildup. In winter, the opposite problem emerged. The steel conducted heat away rapidly, making the huts difficult to warm. Small stoves helped, but fuel was often scarce, and soldiers frequently slept fully clothed under multiple blankets. Condensation remained an issue in humid climates. Warm air from human respiration would condense on the cold steel interior, creating a damp environment that encouraged mould and rust. Some crews addressed this by hanging canvas or burlap inside the hut to catch condensation, but it was an imperfect solution. Despite these limitations, the Nissen Hut succeeded because it solved the fundamental problem. Soldiers had shelter. They weren't sleeping in mud. They weren't dying of exposure. And when a position needed to be abandoned, the huts could be disassembled in a few hours, loaded onto trucks or trains, and reassembled elsewhere. By the time the armistice was signed on November 11, 1918, over 100,000 Nissen huts had been manufactured. They stretched across France, Belgium, and Britain, forming instant towns wherever the military needed infrastructure. After the war, the British military faced an unexpected surplus. Tens of thousands of Nissen huts sat in depots and fields, no longer needed for their original purpose. Rather than scrapping them, the government sold them to civilians at remarkably low prices. A complete hut cost less than £50, cheaper than building a comparable wooden structure from raw materials. Veterans returning from the war purchased them by the thousands. In Britain, they became temporary housing for families displaced by wartime bombing. In rural areas, they served as farm buildings, storage sheds, and workshops. Churches bought them for community centres. Schools used them as temporary classrooms, while permanent buildings were under construction. The Nissen Hut, designed as a military expedient, became a fixture of post-war civilian life, but the design's greatest test was still ahead. In 1939, when war returned to Europe, the British military immediately ordered renewed production of Nissen Huts. The design had proven itself during the last war, and military planners knew they would need mobile shelter infrastructure on an even larger scale. By mid-1940, production was underway at facilities across Britain. This time, manufacturers had 2 decades of experience refining the basic concept. The corrugated steel was slightly heavier gauge, more resistant to corrosion. The wooden ribs were replaced with steel ribs, stronger and more durable. The assembly process was further standardized, with pre-drilled holes and numbered components that reduced construction time even further. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Second World War deployment of Nissen Huts dwarfed the First World War numbers. Over 200,000 huts were manufactured between 1939 and 1945. They appeared on every front where British and Commonwealth forces operated. North Africa, the Mediterranean, Southeast Asia, the Pacific, and eventually across Europe following the D-Day landings. In the Western Desert, Nissen Huts housed the 8th Army during the campaigns against Rommel's Afrika Korps. The steel shells absorbed punishing heat during the day but cooled rapidly at night, making them more comfortable than canvas tents in desert conditions. In Burma, they served as field hospitals for wounded soldiers evacuated from jungle combat. The curved steel roof shed monsoon rains effectively, keeping medical equipment and patients dry even during the heaviest downpours. In Britain itself, thousands of Nissen Huts formed the backbone of training camps where millions of soldiers prepared for deployment. Rows of identical curved shelters stretched across former farmland, creating instant military cities that could house 50,000 men. The huts also served more specialized purposes. RAF bomber bases used extra-large Nissen designs as aircraft hangars, with curved steel arch spanning 60 feet to accommodate Lancaster and Halifax bombers. These hangar versions used heavier gauge steel and required more substantial foundations, but the basic principle remained unchanged. The self-supporting arch needed no internal columns or truss, leaving the interior completely open for aircraft maintenance. American forces, observing British use of Nissen Huts, developed their own variation called the Quonset hut. The American design incorporated several improvements based on lessons learned from the original Nissen concept. Quonset huts added vertical side walls before the arch curve began, reclaiming floor space that was wasted in the pure semicircular design. They used lighter materials and more sophisticated fastening systems, reducing both weight and assembly time. But the fundamental principle, the self-supporting curved arch, came directly from Peter Nissen's 1917 prototype. By the end of World War II, Nissen and Quonset-style huts had housed more soldiers than any other shelter design in history. Conservative estimates suggest over 5 million men lived in these curved steel structures at some point during the war. They weren't comfortable. They weren't permanent, but they were there when needed, built quickly, transported easily, and serving their purpose reliably under the most demanding conditions imaginable. The post-1945 world saw another massive surplus of military huts. Britain, America, Canada, Australia, and New Zealand all faced the same question. What do we do with hundreds of thousands of steel shelters we no longer need? The answer was civilian repurposing on an unprecedented scale. In Britain, Nissen Huts became emergency housing for families whose homes had been destroyed during the Blitz. Entire neighbourhoods of curved steel shelters appeared in cities like London, Coventry, and Liverpool. They were meant to be temporary, a stopgap until proper housing could be rebuilt. Many remained occupied for decades. Universities bought them for student housing to accommodate returning veterans, taking advantage of education benefits. At Oxford and Cambridge, rows of Nissen Huts appeared on college grounds, creating a jarring contrast between medieval stone and 20th-century corrugated steel. Students complained about the cold and the noise when rain hit the metal roofs. But housing was scarce, and the huts provided shelter for thousands of young men who might otherwise have been unable to pursue higher education. Farmers discovered that Nissen huts made excellent barns and equipment storage. The open interior, free of supporting columns, could accommodate tractors and harvesting machinery. The curved roof shed snow and rain efficiently. Best of all, they were cheap. A farmer could buy a surplus military hut for the cost of a few months' wages and have a structure that would last 50 years. Industry found users as well. Small manufacturers bought Nissen huts for factory space, installing machinery inside the curved steel shells, and discovering that the simple arch design actually provided good acoustics and natural ventilation. Light manufacturing, particularly metalworking and woodworking shops, thrived in converted military huts throughout the 1950s and 60s. Even churches embraced the design. Congregations too small to afford traditional buildings purchased Nissen huts, added cross to the end walls, and held services inside structures that had originally housed soldiers. The curved ceiling, some priests noted, had a peculiar acoustic quality that made singing sound richer, more resonant, as if the steel shell amplified human voices. Peter Norman Nissen lived to see his design become one of the most reproduced structures in history. After the First World War, he returned to Canada, resumed his engineering career, and largely stayed out of public attention. He received modest royalties from manufacturers who licensed his design, but the British military had secured the patent under wartime emergency provisions, limiting his financial benefit. Nissen never complained publicly. In the few interviews he gave later in life, he expressed satisfaction that his concept had saved lives and served its intended purpose. He died in 1965 at age 79. Long after Nissen huts had become simply part of the landscape, so common that most people no longer thought about their origins or the engineering insight that had made them possible. The curved steel shelter, born from desperation in Belgian mud in 1917, had become timeless. Today, over a century after Nissen stood in that muddy field at Ypres, the huts remain. Thousands survive worldwide, repurposed and renovated, serving functions their designer never imagined. In Britain, they're community centres, storage facilities, small businesses, and even residential homes. Some are protected as historical structures, preserved as reminders of wartime innovation. The design itself influenced architecture far beyond military applications. The self-supporting arch, the use of corrugated metal for both structure and skin, the principle of prefabricated modular construction, all became standard techniques in 20th century building. Modern barrel vault roofs, Quonset-style commercial buildings, and contemporary prefab housing all owe something to Nissen's basic insight, that a simple curve, properly executed, can be stronger than complex engineering. The mathematics of the arch had been understood since Roman times. The Pantheon in Rome proved that curved structures could span enormous distances and survive millennia. What Nissen contributed was the democratization of that principle. He made the arch accessible, portable, and simple enough for ordinary soldiers to build with hand tools. In doing so, he created a shelter that saved countless lives and proved that revolutionary design doesn't require complexity. Sometimes it requires only the courage to abandon traditional thinking and trust that geometry, properly applied, will do the work. The legacy of the Nissen hut extends beyond simple numbers of units produced or soldiers housed. It represents a fundamental shift in how military organizations approach the problem of infrastructure. Before 1917, armies built for permanence even in temporary situations. Heavy timber barracks, concrete foundations, traditional construction methods that assumed stability and time. Nissen proved that military infrastructure could be as mobile as the troops it served. The hut wasn't tied to a specific location. It existed as a concept, a set of components that could be assembled wherever needed and disassembled when circumstances changed. This philosophy influenced military thinking for generations. Modern deployable shelters, from inflatable structures to containerized housing units, all descend from Nissen's basic insight that shelter should move with the army, not anchor it in place. The technical elegance of the player repeating a design lay in its refusal to fight physics. Traditional buildings resist wind, snow, and rain through mass and strength. The Nissen Hut deflected these forces through geometry, wind hitting the curved surface split, and flowed around the structure rather than pushing against a flat surface. Snow slid off the smooth arch rather than accumulating weight. Rain ran down the corrugations and dripped to the ground rather than pooling and creating leaks. This principle of working with natural forces rather than against them became fundamental to 20th century engineering. Aircraft fuselage, ship hulls, even automotive design embraced the lesson that curves distribute stress more efficiently than angles. Nissen wasn't the first to understand this, but he was among the first to apply it to mass-produced, utilitarian structures where elegance of form served practical function. The human dimension of the story matters as much as the technical achievement. Nissen wasn't a career military officer seeking promotion or an industrialist pursuing profit. He was an engineer who saw a problem and solved it using first principles thinking. The British Army, desperate enough to try unconventional solutions, gave him freedom to work. The result changed how armies built shelter for the next 100 years. Sergeant Davis and his crew, standing in Belgian mud in September 1917, didn't know they were building the prototype for a design that would house millions. They just followed instructions, bolted steel to wood, and went home at sunset, having completed something that looked strange but worked perfectly. That ordinariness, that accessibility to common soldiers with common tools, was exactly what made the design revolutionary. Up next, you've got 2 more standout stories right on your screen. If this one hits the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.